of the system, we get the opcodes, and we get a disassemble of the opcodes. And for those instructions that got lots of stars, remember that this is x86, so basically every instruction may have thousands of loads and thousands of stars. We get the loads and stars later with the virtual and physical addresses and the length of the axis. Okay? And that is basically the information that is going to be sent to the memory modules if you ever get a memory module, which we'll see later. Okay. So, yeah. So this. Okay. So yeah. So this was a very simple example. So now we're gonna try to program a more complicated CPU timer, and we hacked up an in-order timer. So we can go to the SDK, and we can open this. Okay. So there's a namespace here that, there's a namespace, an anonymous namespace here that we're not going to talk about that have lots of utilities, but this file has got 365 lines, so it's not very big. You don't expect anything like too complicated from this timer, but it's a very simple timer. And it shows what you can do, and it shows the memory. So notice that this is more or less exactly the same, but now we have another extra function which is called the add memory. This is going to be called by Lua every time that someone from Lua wants to give you a memory module. And we'll see examples of how to put your own memory hierarchy here. Then we're going to have pointers to those memory modules, to the iCache, the date cache, and TLDs. And we're also going to have a couple of parameters that control how this model works. This is very similar to what an in-order, simple scalar in-order does. Here, it's basically the same. You give your parameters from your table, and we'll see how this are put. You put your own parameters here, and you add your external outputs. Here, the external outputs are much easier. If you basically just publishing your IPC and instructions, you probably would want to have here more information about how many times your reorder buffer was full, how many times it was half full, or whatever. And we basically clear that out from this example. And here you get the simulation kind of function. You accept an instruction, and you add it to a waiting instruction table, and every time that you get enough instruction, that you get more than one line of cache in that instruction table, you simulate one cycle. Notice that here we only increment the amount of cycles every time that so we may be executing more than one instruction per cycle. And each one of these functions, commit stage, memory stage, and fetch stage, are explained just under the name. So the fetch stage is very simple. We basically assume a maximum amount of instructions that we can fetch, and we fetch as many as we can if we are hidden in cache. So we could be waiting for cache, and in that case we just return and we don't do anything, or we could have the reorder buffer full, and if the buffer is full, we don't insert new instructions to the reorder buffer. But if not, we just basically decrement one instruction and we get the next PC, we read it from the instruction cache, we add we know if it's a hit or a miss, and if it's not a miss, then we wait, or we don't wait, or we add it to the reorder buffer. So it's a very simple implementation. Here, the memory stage is basically, so this is a 3-stage pipeline. The memory stage is the execute. We didn't put a decode stage or a renaming stage, but you can add those stages later and build this up. And basically, we go through all the loads and stores of the application, and we execute them to the cache if there are ports available. And if there's any kind of miss in the cache, we add that where something here, we put the latency of this particular load, and we won't finish this load until the latency has arrived, and blah blah blah. So it's very simple. And at the commit stage, basically we commit as many instructions as the architecture lets us, which is max commit per cycle if they are finished. So as you can see, this is a very simple in order, and we can use it. And this is the other function that I wanted to show you, which is the add memory. This is going to be called externally from Lua. Well, this is Lua sends you the memory modules for you to work. And so this is a really kind of a more interesting one. Notice that we're also only simulating one sample, and we're also simulating with a simple sampler. This is like very trivial. We only want one file at the end with all of the results, which in this case would be equivalent, because since we only have one sample, we're only going to get the last one, and we're going to get more than one. And we use basically the same infrastructure as before, except that currently we are getting an input file, and we're executing that input file. Remember that X-tools are the tools that allow Signal to communicate to the serial. It's basically XGet and XPut are basically ways of copying files in and out. Although this file here is, the simulation is so small that I don't think that this is going to do anything, but we'll see it later. And let's see if this fits from Windows. Okay, it doesn't fit. Okay, so for here it's a little bit more complicated. For each CPU we get the CPU object from COTSon, and we build a timer which is a specific in-order timer. That in-order timer needs a couple of parameters which we didn't give any kind of default values before, so we have to put them all here. So the buffer, the buffer size, the max commit size, whatever you want. Of course, in your model you can make something have a default, so the user doesn't have to put it always. And then what we do here, this kind of architecture is the one that we're seeing over there. And one of the good things of having a language like Lua here is that you can put any kind of memory hierarchy that you want. Notice that we are building, that we have an instruction cache and a data cache, and with all the parameters, right policy, right allocation, whatever, and we're making them point their next pointer to the L2, which we put here, exactly here. So basically, in the other side means that each one of this particular VSD has two CPUs. So each particular CPU is going to have an instruction cache and a data cache, and it's going to have a private L2. Had we put, and over here we are doing something very similar with the TLDs, the private TLDs. Had we put the L2 outside this loop, means that there will be a shared L2 for all of them, which is exactly what we have here with the noisy bus. So notice that the L2 has an X that points to the bus. And the bus is an object that we just created, a Lua object that we just created here, which named bus. The protocol is messy, latency, bandwidth, all the parameters that bus really needs, and that points to main memory, which is the simplest of all, which basically has no latency. Had we put the L2 outside, it would mean that those two L2s would be at one unique L2, and all the L1 caches would point to that. So it's very simple to build your own memory hierarchy and build your own memory modules and have more stuff being done. And we'll put, in the following examples, we'll put another fake, well, we'll tell you how to do more interesting stuff. Okay, so now that we have this, we can run it. And okay, this is non-interactive, the same as before. And it takes a little bit more because the BSD is a little bit bigger. But once it gets loaded, it executes very simple, very quickly. So we're going to see the output of this. Okay. As you can see, all the parameters that we